The vaccines that end up in our arms tend to look like a boring, clear liquid, but inside there's a lot going on. Today, it's day 63 and I'm joining postdoctoral research fellow Connor Scott to have a peek under the hood, aka down the microscope, into what's going on in a world invisible to the naked eye. Connor is using a transition electron microscope to check the quality of our vaccine candidate proteins Q and Z. These are very high-powered microscopes for viewing super tiny proteins. Instead of using light to view the proteins, like our eyes, or a regular microscope, they use a beam of electrons. I've come up with a bit of a rough analogy to explain why we use electrons instead of light to view our vaccine candidate proteins, and I've recruited my plush E. coli to help. We're going to imagine this is a vaccine candidate protein. You may be familiar with light microscopy, maybe from high school. The main difference between light and electrons that we're interested in when we talk about microscopy is wavelength. Light comes in a range of different wavelengths, from really long radio waves, to red light, to blue light, to ultraviolet light, and even gamma radiation is really short wavelengths. Electrons have even shorter wavelengths than this, and that is the key. I'm going to throw this vaccine candidate up in the air, and I'm going to set my hands to a wavelength. If I set them like this, and we'll call this a light wavelength, when I throw my bacteria up in the air, it lands square in the dirt. Whereas if I dust him off, set my wavelength to be much shorter, when I throw it in the air, I'll catch it again. And that's the key. Because our vaccine candidates are so small, longer wavelengths can't detect them. So we need the short wavelengths provided by an electron in order to get a good picture of what's going on the microscopic scale. Even though electrons are really small, this microscope is one of the biggest, fanciest ones I've seen. It requires lots of moving parts to make sure the electrons hit the samples just right. The little disc Connor is fiddling around with has our vaccine candidates stuck to it. Thousands and thousands of proteins can fit on this disc, which is roughly the size of a pea. Connor is setting up the microscope, which requires a lot of fiddling around to make sure our image is clear. After lots of button pushing, I'm seeing our vaccine candidate proteins for the first time.
You see particles like this that have like a globular head and then a small density next to it, which to me was likely the Chappare GP in the molecular plant.
Feeling a bit cheeky, I asked him whether he thought Q or Z was going to be the better vaccine candidate. Unfortunately, he gave me a very scientific and rational answer, instead of a good YouTube hook.
It's sort of hard to make an on-the-spot decision based off just like a few images. So like best practice is to collect a data set and then process it using a software called Cryospark, and basically from that you can generate those 2D classes.
The vaccine candidate proteins are a three-dimensional object. When we shoot a beam of electrons at them, what we get is a two-dimensional shadow of the vaccine candidate at a particular orientation. When we average thousands of these shadows and put them together, we get a 2D class, which gives us a good idea of the shape of our vaccine candidate protein.
And that gives you sort of a better indication of how the protein is looking.
After a bit of pushing, he tentatively offered his opinion.
But generally, Q does look nicer. Like there's more distinct particles. They don't look as, I guess, they look much more uniform than the other construct, which is labeled Z here.
So, where does this leave us? Our vaccine candidates are looking good, but we won't know for certain whether they're effective until we see the result of our mouse study. Next time we check in, said mouse study will be wrapping up, and we'll have a good idea of whether Q or Z provides that protective, neutralizing immune response against Chappare mammarenavirus. See you next time as we continue our journey from day 0 to breakthrough.